All right, welcome everybody to our last lecture. I hope everybody's project is in good shape at this point. And I sent you a note, but I wanted to advertise once more that so last class we defined the specialization of curvature dimension to Riemannian curvature dimension, which basically means that the tangent cone at almost every point on the metric space is Euclidean. And there's going to be a whole course about Riemannian curvature dimension spaces in the fall by Nicola Gili, one of the inventors of the theory. Fields, I think it will be hybrid style, so I recommend checking it out. And so my agenda for today is I wanted to finish the proof of existence of maps from Monge's solution, minimizing the actual distance cost, which is what Monge wanted to do in the 18th century, and we managed to do in the last part of the 20th century. And then depending on how time goes, I may also show you an application to inequalities if time permits. So are there any questions, problems, or difficulties? So let me basically review where we were at the end of last class. I'd introduced a bunch of notation. So let me remind you how that goes. So we're on a Polish space. Whenever it's convenient, I'll assume it to be compact, but compactness doesn't play a big role in most of what I want to say today. And as long as if I have a function on that space with Lipschitz constant less than 1, I can define a relation, which is basically all those pairs of points such that the Lipschitz condition is satisfied. And we checked last class that this was a partial ordering. And then let me also define its symmetrization. So its symmetrization is the set of points in X2 such that either X dominates Y or Y dominates X. And we can also define its multiplicity points, which are the set of points in X, such that there exists a pair of points Y and Z, which are not related to each other. And either X dominates both of them or both of them dominate X. So those were the multiplicity points. And so at least for when we took Euclidean distance on Rn, I showed that the multiplicity points have Lebesgue measure 0 because they live in the set where the Euclidean distance fails to be differentiable. The Lipschitz function U fails to be differentiable. And so hopefully these multiplicity points are going to be measure 0 more generally. But so we showed that tilde U is an equivalence relation on XU, which is all of X that doesn't have multiplicity. And that's basically the definition of multiplicity set up so that tilde U is an equivalence relation. And so let's denote the equivalence class of X by Sometimes I'll call it QX, but more often I'll call it X tilde. And I'm going to sometimes view that as a subset of XU. And sometimes I'll view it as an abstract point in the set of such equivalence classes. And then thinking of these equivalence classes as being subsets of X, I can metrize that by the Hausdorff distance. And then it becomes a Polish space. Okay. And as long as so now there's two big ifs. So if one of them is more serious than the other one. So if let's fix a Borel measure on X, and let's take it to be finite. Oh, sorry, I just took it to be a probability measure. Okay. So things get a little more tricky if you're dealing, if you have a reference measure with finite total mass, you can always normalize it to be a probability. But things get a little more tricky when you have infinite reference measures like Lebesgue measures on Rn. And there's a trick for handling them, which is basically you multiply it by something that makes it finite, like maybe a Gaussian density, and then you do everything for the multiplied guy, and you show that the multiplication doesn't affect, you can afterwards you can divide out. So, but anyhow, let me not get distracted by that. So if I have a finite Borel measure and the set of negligible points or multiplicity points is negligible, then I can disintegrate M with respect to the map Q that takes points in X to equivalence classes in XU to get what does disintegration mean? It means whenever I have a continuous function that I want to integrate against M, or indeed a measurable function, that I can get the value of that integral by first integrating over points in the equivalence classes with respect to some induced measure, which I'm going to call M tilde. So here, M tilde is going to be the image under Q of M. And then I'm going to have a set of conditional probabilities on the rays. That's a little x. The integral over the ray little x tilde and XU in capital XU phi dm x tilde for every continuous or Borel phi. And so let me pause for a second. Okay, so this is all pretty abstract, but I will give an example in a minute. But before I give the example, are there questions? So notice that if I have, if I want to choose some other measure, which happens to be absolutely continuous with respect to M, I can also disintegrate it with respect to the same quotient map. And if I denote its density by then its disintegration is going to be given basically is pretty related to the one above. So is going to be given by mu sub x tilde, which is basically m sub x tilde, except you want to put rho, you want to multiply by rho. And the problem is that that may not be a probability measure anymore, so you need to divide by a normalization constant. Let's call it z of x tilde. And the thing that plays the role of the projected measure is, let's call it mu tilde, is going to be proportional to m tilde. But in order to sort of, think about replacing phi in this formula by rho. If I want to divide by z in here, that's okay, provided I multiply by z over here. So, so dm of x, let's say, is going to be z of x tilde, dm tilde x tilde is going to be z of x tilde. Okay, great. So that was sort of the framework that I tried to set up last class. So let me give some examples to fix ideas. So the most trivial example is, oh yeah, well, obviously if the Lipschitz constant is less than 1, then that's going to imply that the equivalence relation U is just going to be the set of all points on the diagonal. And so that's very uninteresting. So obviously, if we want interesting equivalence relations, then we're going to want to most look at functions which have slope 1 in the regions of interest. So that's sort of example 0. And another example is, suppose I want to do optimal transportation and I have a measure like on the real line. And I have a measure like the density of the source is going to be, say, the characteristic function of the unit interval, and the density of the target is maybe the characteristic function of the interval minus r0 plus the characteristic function of the interval 1 plus r. So r should be between 0 and 1 here. And so the picture is that my source looks like this, and my sink looks like that. Sorry, things don't add up very well right now. So, so if I want to make this add up, then maybe I should do 2 minus r, would have been fine. So if this is 2 and this is 1, so I should put 2 minus r here. So it's pretty clear what I want to do in this case. So I need to take the left fraction r here and shift it to the left, and the right fraction here and shift it distance 1 minus r to the right. And and then it doesn't matter actually whether I orientation reverse when I'm shipping this or orientation preserve, as long as I measure preserving. But the optimal Lipschitz function, the Kantorovich potential, if you like, is going to be given by basically, I guess, x minus r, negative of that. So it's going to be a function that around the splitting point, it has slope 1 in either direction. And so you see that all the points, so x is going to be related to y if and only if either x and y is in r to infinity, or x and y is in minus infinity up to r. This is the only multiplicity point here. Maybe I should have done this. I should have put closed intervals. So I have to get rid of this multiplicity point in order for these equivalence classes to be disjoint. So all the x's on the right of r are equivalent to each other. All the y's on the left of r are equivalent to each other. And I need to discard the point r. And so you see it has, in this case, at a 0 measure. And another example, which is maybe nice to keep in mind, is take capital X to be the boundary of the unit ball in R3, let's say. And just with the round metric. And then if you take, if you fix north and south poles, and you take your function u of x to be maybe the distance to the south pole, then the multiplicity set is going to be the north and south pole. And the equivalence relation is going to basically, the equivalence classes are going to consist of the picture of the sphere is like this. You have a multiple point here, a multiple point here. The Lipschitz function increases at rate 1 as you go from the south pole to the north pole along any meridian of longitude. And so the equivalence classes are going to be meridians of longitude minus the north and south pole. Okay. And then I got all tangled up proving some elementary claim. So let me come back to the claim that I put on hold last lecture. And let me prove a simpler claim first. So I'd already shown that if x naught dominates x1 in any order, in one of these orders for a Lipschitz function u, then the entire geodesic xt has the property that xs dominates xt for any s less than t. And let me now place, I'll call this claim, this is a modified claim, so it doesn't really fit in the numbering scheme from last time around. So maybe I'll call it claim 2 prime. It's a kind of partial converse to this. So conversely, if I have 3 points in order, x dominating y dominating z, then basically dxy plus dyz saturates the triangle inequality. And so this, let me prove it. It's really easy to prove. So x dominating y means that, so all of these proofs, they basically are playing off the triangle inequality on the one hand with the Lipschitz condition on the other to show that equality holds. And So x dominating y says that ux minus uy is dyz, dxy rather. And y dominating z implies uy minus uz is dyz. And so you add these two things up, and the uy terms cancel, and you get ux minus uz is equal to dxy plus dyz. And the triangle inequality says that that's says that that's bigger than dxz. This is the triangle inequality. And on the other hand, the Lifshitz condition says that this is less than dxz, the one Lifshitz condition, and so equality has to hold throughout. And a corollary is that x dominating y dominating z implies y lies on a geodesic. Joining x to z if xd is a geodesic space. But the more interesting corollary, the thing that I'm really interested in is that I stumbled on last class, is that if x dominates y dominates z, any existing geodesics linking x to y and y to z, d-geodesics, can be concatenated, and that the resulting thing that you get from concatenating them is again a d-geodesic. Joining x to z. And this is sort of, when you try to prove this corollary, it's a little bit fiddly. And so let me not try to prove the, let me do a special case. So let me say it's fiddly. You know, if you have parameters saying, so you have the picture is I have a geodesic joining x to y and another geodesic joining y to z, and I want to know that I can concatenate them and get it. So let's focus on midpoints. So it's fiddly in general. So focus on midpoints, and we'll show the midpoint case at least. So I'm going to assume, let's say I'll just normalize it so that the distance between x and z is 1. And I know by the previous corollary, I know that the distance from x to y and y to z has to add up to 1. And so to focus on midpoints, I'll assume that the distance xy is equal to the distance yz, which is therefore equal to 1/2. And suppose I have further midpoints. The midpoint between x and y I'll call u, or maybe use bad notation, I'll call v, and the midpoint between y and z I'll call w. So if dxv is equal to dvy is equal to, I guess, 1/4 in this case, and the same thing for dyw and dwz, what I need to show is that the distance between v and w is 1/2. And of course, obviously, the distance from v to w is less than the distance vy plus the distance yw, and these are each 1/4. So obviously the distance is less than 1/2, And so I need to show that it's bigger than 1/2. That's what I would expect if this whole thing is really a geodesic and not strict, not that there's, so what I want to rule out is is that there's some shorter path elsewhere joining V to W. And so how do I rule out that there's some shorter path elsewhere? I know that U is increasing at rate 1 along this segment here from, so it changes by 1/4 going from V to Y, and it continues to increase, or sorry, it's decreasing. So it's highest here and smallest there. So it's decreasing, it decreases by 1/4 going from V to Y, it decreases by another 1/4 going from Y to Z. So, so UV minus UY is 1/4, and UY minus UZ is 1/4 along the existing geodesics. Right, it can't decrease at rate faster than 1 because it's Lipschitz, and it needs to decrease at rate 1 all the way from X to Z for the distance XZ really to be 1/2. And so I add these things up and I get U of V minus U of Z is 1/2. And by the Lipschitz condition, that's less than the distance from, this should have been W. The distance from, this should have been W. The distance from V to W. And that's what I want. So I'd already shown the distance from V to W was less than 1/2 here. And now I've shown it's bigger than 1/2. And you can make the same, if you had chosen a different, if you had chosen Y further along and V and W that divided these into different proportions, you can make the same argument work, but then you just have all these constants floating around, the ratio that Y divides XZ into, the ratio that W divides XY into, and the ratio that that W divides YZ into. Okay. And so now I'm in a good position to try to describe the equivalence classes in a general geodesic space. So now I'm able to do claim 3, which was the thing that I had trouble with last class. If I have a Polish geodesic space, and as usual, I have a Lipschitz function with Lipschitz constant less than 1. If X dominates Y, dominates Z, that's a spurious mark there. Then either all 3 points lie on a single D geodesic, or Z is minimal in the ordering, or there's a geodesic which branches. There is a geodesic through Z which branches with X on one branch and Y on the other. And so, for example, if I'm in a non-branching space, then I can rule out C right away. So unless B holds, there exists a W which is less than Z in the ordering. And so because I'm a geodesic space, so my picture is X is bigger than Y in the ordering, and Z is bigger than Z in the ordering, and Y is bigger than Z in the ordering, and there's a W somewhere else that's less than Z in the ordering. Because I'm a geodesic space, there's a geodesic segment that connects Y to Z, there's a geodesic segment that connects Z to X, and there's a geodesic segment that connects Z to Y. And by the previous lemma, since X dominates Z dominates W, the geodesics linking X to Z and Z to W can be concatenated. So in other words, to form a new geodesic. So in other words, the concatenation of this with this is a geodesic. And similarly, the concatenation of that with this is a geodesic. And so I've just constructed a branching geodesic. Oh, sorry. Well, yeah, so I shouldn't say that quite yet. So there are two possibilities. So the resulting two geodesics, either one is a subset of the other. In which case A holds, all 3 points are on the same geodesic. Or else there must be somewhere, one doesn't contain the other, so they don't necessarily branch at Z, they might branch further up, but somewhere there's a branch. Somewhere above Z, in which case C holds. Is it clear? All right. And so we did this kind of with minimal elements, but I could do the same thing with maximal elements instead. If I had a Z dominating both X and Y, then either it would be a maximal element or there would be a branch geodesic where all 3 points would be on the same and so we saw in the sphere example was, there was a maximizing element, there was maybe a maximizing element in the South Pole and the minimizing element at the North Pole, and then there were all these different equivalence classes, all of which ended at the two maximizing and minimizing elements. And so then a corollary of claim 3 is that shoot, I have a better version of this somewhere, but I didn't print it out. Let me take a look at my better version so I can make a better statement. Right. So the equivalence classes are called rays. And the corollary is that the multiplicity points, mu consists of all points lying below in the first example or above a branch in a geodesic. So in other words, if you increased at rate 1 along a geodesic that looked like this, all of these points down here would get discarded because they're multiplicity points. Together with minimal or maximal. And similarly, if you increased at rate 1 along these two guys, then this endpoint would be a multiplicity point, but it's a minimal element in the ordering. Minimal or maximal elements belonging to more than one ray. The closure of more than one ray. And that's basically everything. And so therefore, if that's basically everything, thus rays consist of d geodesics minus one or both endpoints. Okay, so let me try to argue this for a minute. And it follows from claim 3. So given a point in an equivalence class, any finite collection of points dominated by X or dominating X, or all dominating X, all dominated by X or all dominating X, lie on a single geodesic. I should have said points in XU or in X tilde. And moreover, because I can join the two geodesics, so I can sort of, the geodesic for those lying above X and the geodesic for those lying below X can be joined to get a single geodesic. So therefore, I can now remove this all dominated by or all dominating X. And what else do I want to check? I want to check that X tilde is closed. So also any limit point X tilde, which lies between a higher and lower point let's say any limit point y of x tilde, which lies between x and z in x tilde. Because, so what do I want to rule out that this has multiplicity. If it has multiplicity, then, I want to rule out that y has multiplicity. Cannot have multiplicity. Right, so what would it mean that y had multiplicity? It would mean that y, let's say, y would be dominated by two other guys, v and w, and then I would get a branch geodesic from x through y to v and from x through y to w. And what would be wrong with that? Why can't it have multiplicity? Yeah, then I would have, then everything below y would have multiplicity as well. So x would have multiplicity. So x would not be in, it would not be in the set of points. Which, is that clear? Or do I need to say more? Kind of clear. And so therefore x tilde, apart from perhaps its endpoints, so rather x tilde minus the closure, or rather the closure of x tilde, closure of x tilde minus x tilde is contained in the least and greatest elements with respect to the ordering. And okay, so now we have some object, and any finite number, it's a closed object apart from possibly these two extreme elements, and any finite number of the points on the objects lie on a geodesic. And so by compactness of the closed sets, of the closed subsets of X with respect to dH, the whole thing must be a geodesic. Maybe what I'm really using is compactness of the set of geodesics with respect to the sup norm. Okay, so great, so we're in good shape. And so I had kind of already, so more or less the picture is now, so I now want to solve Monge's problem. Solving Monge's problem on Rn, or a compact Riemannian manifold. Probably for simplicity, I would assume the measures to be compactly supported if I wanted to work in Rn. So I would actually work on a big compact ball in Rn. So to do this, I'm going to let, I'm going to first let mu plus and minus be probability measures, but they're going to be absolutely continuous and compactly supported with respect to Lebesgue measure. And I'm going to choose an optimal joint measure and a Lipschitz function u, which are d-optimal, dual to each other. And I'm going to construct this equivalence, this partial ordering and equivalence relation induced by U. And the picture is that somehow M plus lives over here and M minus mu minus lives over there. And the Lipschitz U is decreasing at maximum rate under a bunch of rays like this, which don't cross each other. And the idea is I disintegrate these two guys. So this would be an equivalence class, and I get a measure mu plus x tilde on this equivalence class, and a measure probably living over here, mu minus x tilde on this equivalence class. And I would do the monotone non-decreasing map on each equivalence class, and then I would glue all those things together, which pushes forward this to that, and I would glue all those things together and hope to get a mapping G from Rn to itself, such that G pushes forward mu plus to mu minus, built from its restrictions to x tilde and the restrictions are, let's call the restrictions gx tilde, and the restrictions gx tilde are basically given by f mu x plus composed with f x tilde minus x tilde inverse, where these are the cumulative distribution functions. I could choose it to be open or half closed as long as I'm consistent. For 1D measures. So that was the strategy. And what I need to make in order to make this strategy work is I need that whenever I take a collection of these equivalence classes whose union is measurable, let's say Borel, the total amount of mu plus mass on that union is equal to the total amount of mu minus mass. So in other words, when I do these disintegrations, so I need the mu plus tilde and the mu minus tilde to agree with each other when I do this, when I disintegrate. I.e., remember, when I disintegrated a measure mu that was absolutely continuous with respect to m, the conditionals of mu were the conditionals m multiplied by the Radon-Nikodine derivative, but I had to divide by a normalization constant, and I want that normalization constant to be the same for when I decompose mu plus and mu minus. Let's say, I don't know, mu plus minus tilde almost every x tilde. And so where does this come from? That's what's that would be called, I guess, localized mass balance. And so that's going to come from the following lemma, which I think Feldman and I call it detailed mass balance. So the difference between detailed and local is that when I look at detailed mass balance, I take a collection of rays whose union has positive measure for both mu plus and mu minus, let's say. And when I talk about local mass balance, I've done the disintegration, and so I'm looking at a single ray. But it's clear that if every collection of rays with positive measure has the same amount of mu plus mass and the same amount of mu minus mass on it, then each single ray, then basically these quotient measures are going to have to agree. So So let sigma tilde be a collection of equivalence classes such that the union of equivalence classes in the set is Borel, or even gamma. Yeah, so did we take an optimizer? We did. So I'm dealing with this optimizer and that U. Is gamma measurable, or Borel would certainly be enough. Wait a second. Something is, let's say Borel. Let me not try to be fancy. And then I claim mu plus of sigma equals mu minus of sigma. That's what I want to prove. And the proof goes the following way. So again, let gamma mu plus and U, and it's negative BD optimal. And then we know that duality showed that gamma vanishes outside this equivalence relation. And so, and on the other hand, if I take this set of rays and this set of full measure, so maybe I should have said provided the mass of the multiplicity points is 0. So provided the multiplicity points are negligible, which we know is true in Euclidean space, this is a set of full measure and for mu plus. And if I intersect that with the, or for mu minus, whatever, if I intersect that with the partial ordering, then I get the same thing as if I reversed the order of the factors. Right, because if my lower point is on one of the preferred equivalence classes, and my upper point doesn't have multiplicity, and sorry, if my upper point is on one of the preferred equivalence classes, my lower point doesn't have multiplicity, and they're in relation to each other, then that also means that the lower point is on the same equivalence class. And so now if I apply gamma, this is a measure 0, and so I get gamma of sigma cross U is equal to gamma of XU cross sigma, but this is mu plus of sigma, and this is mu minus of sigma, because those were the marginals. Any questions? So that says when I do this disintegration of mu plus and mu minus, the quotient, the conditional marginals are different because the conditional measures of mu plus live over here and the conditional measures of mu minus live over there. But the overall measure that governs the weights of the different rays in the equivalence class, which basically have to do with, yeah, okay, are the same. And so now I'm in great shape. Oh, I'm in great shape, except for I still need to prove. So the remaining obstacle is I need that if x tilde is not equal to a single point, then mu tilde, which is the common measure, almost surely mu plus, let's say, is atom-free. Restricted text tilde is atom-free. This was the obstacle that Sudakov's proof broke down on that I mentioned last class. And so the way Feldman and I resolved this in Euclidean space was we actually proved much, much more is true. So we did a lot of work. But let me show you the idea. So the idea is if all, so u is large over here and u is small over there, it's decreasing along these rays. And so the idea is to do a change of variables, which in a perfect world would be by Lifshitz, which takes a level set of u, let's say u equals constant or u equals 0, and flattens it out into a copy of Rn minus 1. And then we extend the rays parallel to that. And so the mapping would take the level, if you're on the level set, it would go to the R minus 1. And then if you're on one side or the other side of the level set, it would go whatever the distance is along this ray, it'd go that far out into Rn. And so we call this ray flattening maps or ray parallelizing maps, paralleling, so flattening maps. And if you can actually, if the flattening map were actually by Lifshitz, then the Jacobian of that flattening map would be giving you, you'd be able to read these disintegrations off explicitly. So in fact, when Feldman and I did this, we didn't know anything about disintegration. And so we instead of appealing to an abstract theorem saying that the conditional probabilities exist, we actually constructed the conditional probabilities using the Jacobian of this Lipschitz flattening map.
Did the reviewers tell you about?
No, the reviewers didn't. I say Feldman and I. This was a paper with Caffarelli, Feldman, and myself, and on Euclidean space, and then in Riemannian manifolds, Feldman and I did that without Caffarelli. And now the problem is that, of course, you can't. So it could be that the ray structure is very complicated, and you have a lot of very short rays amongst long rays, and so on. And so you can't actually achieve what I just described with a single flattening map. But you can decompose the rays into countably many clusters, whose union is the whole space, or at least all the parts of the space that you care about, and such that each cluster admits one of these Lipschitz flattening maps. And so you construct the map G separately on each cluster. And again, the key thing is knowing that as you move along this level set of U, that the ray directions are varying in a Lipschitz continuous fashion. And that will be true. When does it fail? It would fail like at the origin if you looked at the distance function, that now the rays are going all directions from the origin. So it's true that the ray directions vary in a Lipschitz fashion if you're not interested, if the ray is not starting or ending on that level set. And so the theorem that I proved with Caffarelli and Feldman, and I guess other people had their own approaches, Trudinger and Wong and Ambrosio had their own approaches about the same time, was that we can decompose Rn into countably many ray clusters with the ray directions varying, I don't know how to say that. I'm saying this in a long and clumsy way. Lipschitz continuously at least away from ray ends. That's not really a theorem, it's a technique. But so how do you do? So let me say how the proof works. So you enumerate the rationals, and then you consider all rays that intersect the set U of X equals QI in their middle third. So you look at some level set of the potential, and you look at rays which intersect it, and not too close to the ends, so the ends are well away. And then the claim is that that the potential, the level set of the potential is actually Lipschitz, I guess Lipschitz. And the ray directions are varying Lipschitz continuously along it. And why is this true? I had a lemma here somewhere. Yes. So i.e. the length of x tilde is oh, and they shouldn't be too short rays either. So the length of x tilde would be, say, bigger than 3r for all these not too short rays. And so what's the basic idea is that so the function u along one of these rays is decreasing at maximal rate, and it can also be touched. It can also be at every point it can be touched from above by a cone whose end is at least r away. And similarly, because v was minus u and it had all the same properties, it can also be touched from below by a cone whose endpoint is at least r away. And so so here u agrees with both an inf and a sup of distance functions centered at least distance r away. And then the observation is that if you look at a distance function, so in other words, if you take f to be the distance, the Euclidean distance to x, to 0, let's say, let's take f to be absolute value of x, then the derivative of f is actually a Lipschitz function outside a ball of radius r. So therefore f, if you like, is it's both semi-concave and semi-convex outside the ball of radius r. And so in other words, u is both semi-concave and semi-convex, which means it's C11, or at least u could be so around in the middle third of this thing, or at least on this set here, u agrees with a C11 function in the whole of Rn. And so that means in particular, gradient u is Lipschitz. And gradient u points along the rays. So the ray directions vary Lipschitz continuously. So that's what allows us to build this Lipschitz change of variables. And that's what implies that mu plus of x tilde has a continuous density, is absolutely continuous with respect to H1, and so therefore atom free. If x doesn't equal a single point. So there can be some rays of length 0, and that just means the mass doesn't move at those points, but obviously those are not the points that I'm talking about here. And then once you have that, Sudokhov's construction that that I talked about last class works, it just works. Or to say it another way, you do the construction that I described along rays, and you patch them all together, and you check that the map that you get has the property that now u of x minus u of gx tilde x is equal to the distance between x and gx tilde x for, I don't know, I guess mu plus x tilde almost every x. And when you integrate this, since u is a Lipschitz function, you find that G is an optimal map. The other thing you have to check is that the G that you get by patching all these things together pushes forward mu plus to mu minus, but it's doing this on rays. And because the mu plus is basically d mu tilde, which doesn't depend on plus or minus, integral d mu plus tilde x on every ray, you find that when you patch these things together, you get the push forward property without restricting to rays. Okay, so I think that that's somehow the outline of the whole proof. Questions? There was one more thing that I wanted to show you. I guess I still have, let's say, 15 minutes, and I think I can do it in 15 minutes. So it relies on one article of faith, and the article of faith is that, let's say I'm in a non-branch space, I still need to know that the multiplicity points have measure 0. And Cavalletti claims this is true. And he also, and probably he did this in his thesis work, part of which was published with Bianchini. And he claims it's true, even it doesn't have to be non-branched, it can be essentially non-branching. Okay, so let's take that article of faith. And then the other thing that Cavalletti shows, and this is fairly straightforward, is that XDM belonging to CDKN implies a couple of things. It implies the one we just said, and it also implies that for M tilde almost every X such that, which is not array of length 0, that the measure is again absolutely continuous with respect to H1. And that then if you look at this ray, which is this one-dimensional geodesic, possibly minus endpoints, and you put the Euclidean distance on it, and you put mx tilde on it as its measure, so that's a one-dimensional space now, that will also be CDKN. So in other words, these one-dimensional factors inherit the entropic convexity properties of the original multi-dimensional space. And morally, I think this, you'd kind of expect that morally that this is if and only if. I'm not exactly sure what the reference would be for the reverse direction, but I can say in a word why. So again, this is all going to be a little bit impressionistic. So what does it mean to be, it means, how do we check the Kn convexity of XDM? We check that, we look at the entropy, which is integral rho t log rho t dm along any geodesic. So if this is a geodesic in the probability measures, we need Kn convexity. normalizing K by the length of this entropy. And our decomposition formula, our disintegration formula tells us that that can also be written as dm tilde over x tilde u integral over little x tilde rho t log rho t dmx tilde, where these are the conditional measures and this is the quotient measure. And so on the one hand, if this thing is a convex function of t, then you're averaging with respect to a probability measure. Maybe I should have said I probably want to normalize these spaces to be safe. Then I'm averaging all these convex things, I get a convex thing again. More or less, that's the spirit of one direction. And the other direction is I have this cluster of rays associated to my whatever Lipschitz U I've chosen, one Lipschitz U I've chosen. And if I localize my measure to be, transport a small ball around one of these rays to whatever it transports to, it's going to stay nearby. And in the limit, as I localize this transport, so the measure vanishes everywhere except in some neighborhood of one of these geodesics, this quantity here is going to be totally dominated by something on one of those geodesics. So that's why I would maybe expect this to be true. And the kind of problems you worked on the third problem set are a bit relevant to adding up Kn convex functions and getting a Kn convex function. So Cavaletti says in a general metric measure space that's essentially non-branching, the space will be CDKN if and only if the factor measures for any one Lipschitz functions are CDKN. That's not too surprising. I just argued it for you. But moreover, he says that for almost every one of these equivalence classes that doesn't degenerate to a point, the factor measures will be absolutely continuous with respect to Lebesgue. And I just described why that's true in Rn. He says it's true more generally. Okay, so once you have this, geometric inequalities become almost trivial to prove. And so the famous, so my closing application of this technique is going to be the Levy-Gromov-Millman isoparametric inequality. Which I don't have time to do full justice to, but what else should I say before I do that? I should say this idea of decomposing M into these conditional measures and a quotient measure, these conditional measures are sometimes called needles. And they're called needles because they live on one-dimensional objects. The transport rays are all either zero-dimensional objects, single points. The equivalence classes consist either of single points or geodesic segments, possibly -1 or both endpoints. And so they're called needles by Klartag, and this technique is also called localization by Cavaletti, but it's a 1D localization. So the idea is not that you localize around a point, but you localize around individual geodesics. And by choosing the one Lipschitz function cleverly, you can localize around any geodesic that's of interest to you. So what does this say? Really, Levy-Gromov was a theorem about manifolds and positive curvature, and Millman extended it to manifolds possibly with negative curvature and also added a diameter bound, so he got a little bit sharper information. And finally, it was extended to metric measure spaces by Cavaletti-Mondino. And so it's an isoparametric theorem, so it talks about how the boundary of a set is related to its volume in a probability space. So I first need to, let me remind, I'm working with Minkowski capacity, which is a way of measuring the size of boundary. And so in a in a boundedly compact metric measure space, Polish metric measure space, XDM, and I'm always going to normalize with So that's why it originally, I mean, Riemannian manifolds with positive Ricci curvature, as we know, have diameter bounded above by the Bishop-Myers diameter bound. So they're compact, and so you can normalize the volume on them if you want. And given any Borel subset, I want to define the size of its boundary by, I'm going to call it M plus of A. It's a boundary measure, to be the lim inf as R goes to 0 of, I look at an epsilon neighborhood, an R neighborhood of A, and I subtract A from it, and I divide by R, right? So the picture is if A looks like this, I fatten it out to size R, and the measure of the fattening divided by R gives a measure of the perimeter of A. For smooth sets, this equals the surface area of A for a smooth set with respect to the measure M. And what is the theorem of Cavalletti and Mondino? It says if, in addition to all the other nice things that we just asked for, if XDM is CDKN and essentially non-branching, or just non-branching is fine. And always MX is normalized. For every volume fraction between 0 and 1, there is an explicit CDKN measure mu, which depends on all the parameters. So it depends on K, N. Oh yeah, I want the diameter of X to be less than, let's say, 2R. Kn, 2R, and the volume fraction. On the Euclidean interval of length 2R, R can be infinity here. So R can be between 0 and infinity. Such that, oh yes, so what's sometimes called the isoperimetric profile of our metric measure space as a function of volume fraction. So this is the smallest surface area that any set of volume V can have. And it says that this thing is bounded below by some number which by its value in a one-dimensional space. Basically, that's what it says. In a one-dimensional space with this measure mu. So in other words, among all spaces with the parameters Kn, the diameter bound to R, when I look at the surface area of a set A, it's controlled by what the surface area would be on the interval of 2R with some measure mu that depends on these various parameters, and which we know is CDKN, so it has some nice convexity property or log concavity property. And moreover, in the interval, the extremizing set is just a subinterval. So the extremizing set has boundary consisting of a point. So somehow all the complicated geometry of the multidimensional space gets pushed down to the interval. And you can solve these mu KRN are explicitly known and pretty simple. And there's a little miracle that happens when n happens to be an integer, which is that the mu turns out not to depend on d in that case. So when n is an integer and k is positive, then the model space that gives this lower bound actually also coincides with the sphere. And the set A is a spherical cap with the same Ricci lower bound and the same upper dimensional bound and the same the same volume factor. And okay, so maybe I'm not really going to have time to prove it, but the proof is really quite, I have this sort of 1-page elementary proof of this thing that only depends on which only depends on the disintegration into needles. And maybe it's not so implausible that when you want to make this comparison between the perimeter of a set and its volume, okay, let me say what the idea of the proof is. The idea of the proof is to take A and its complement. I'm in a probability space, so both A and its complement have finite measure. The measure of A is V, the measure of its complement is 1 minus V. Put a uniform measure on A and a uniform measure on its complement, and with whatever intensities are necessary to get the same total mass or to make them both probability measures, and then optimally transport A onto its complement. So there's some Lipschitz function whose rays tell you how to disintegrate A and then move them monotonically along the rays to take a uniform distribution on A to its complement. And then the idea is that the ratio, so the idea is that on each of these guys, the fraction of measure inside and the fraction of measure outside is still V to 1 minus V. And so the fraction occupied by A of that is still V. And the total boundary area, there's a Fatou lemma that says when you want to compute this thing, the total boundary area in the space is related to the boundary area on each of the factors. And so that the extremizing case has to occur on one of the factors. And so somehow the spirit of this isoparametric inequality is to reduce multi-dimensional information about the isoparametric profile in several dimensions, in any number of dimensions that you want, under a CDN KN condition, to isoparametric information about one-dimensional probabilities on the interval. So somehow, again, the idea is to use this localization into needles to decompose geometrical information about a space into geometrical information about one-dimensional intervals, equipped with the Euclidean distance, but some non-trivial reference measure, but still with the appropriate KN convexity properties. So I guess that's maybe a good place to stop. Thank you very much for your attention. And thanks for staying with me, the 9 or 10 of you that stayed with me through the entire semester. I'm going to